So I'm looking at the kinetics homework problems part 1. Our previous topic, thermodynamics, is answering the question, will a reaction proceed? Will a reaction go forward at all? And if so, will it throw off heat or will it take heat? Will it absorb heat? This topic, kinetics, is answering the question, how fast will it go? Assuming it goes forward at all, how fast will it proceed? Next week, we'll be talking about the third topic, chemical equilibrium, which is getting at the question, how far, assuming it goes forward, how far will it go? How far will it proceed? Here's an energy diagram for the reaction A plus B yields C. So we plot enthalpy over on the y-axis. We use the capital letter H, and you can say heat if you want. Technically, it's enthalpy. Why do we use a strange word like enthalpy? Because it's energy at a constant pressure. On the x-axis, we're using time, or this is the reaction coordinate. So we start here at this level in terms of energy. A and B are sitting there minding their own business in a beaker. See, this could be hydrogen gas, and that could be oxygen gas, and they're going to combine and form a water molecule and release a lot of energy. We did this in a previous lab where we made hydrogen and then we popped the hydrogen in a test tube. What were we doing? We were actually combining it with oxygen, forming water and energy. So the reactants are sitting up here in terms of energy at this level, in terms of the potential energy of the chemical bonds represented in those molecules, in other words. Okay, when we throw in a match, that goes over the activation energy hump, and then we end up down here with water, and the energy that's thrown off is the change in enthalpy, or delta H. So this would be an example of an exothermic reaction. Endothermic reaction could be going the other way. We're taking water down here, and we're going to use electrolysis, and we're going to split it into hydrogen and oxygen, let's say. So we have to input energy, actually the same amount of energy. There is a small hump called an activation energy hump that we have to get over. While we do this, we split water with electricity. So you put water in a beaker like this, and you put some salt in the water to make it conduct electricity, like washing soda, let's say, and you put a carbon electrode over here and a carbon electrode over there, and you put a plus and minus charge, and let's say you put about 6 volts across those with a battery or with a voltage supply. And then if you put a test tube over each of those electrodes, you will collect pure hydrogen and oxygen gas. You'll collect the oxygen over here at the positive electrode and the hydrogen at the negative electrode. Well, we had to input energy, in this case electrical energy, and that is the amount of energy right there, delta H, that you would have to input. So that's what an endothermic reaction looks like. All right, the next topic is the activation complex. In the reaction A2 plus B2 yields 2AB. Again, we could think of the oxygen and hydrogen coming together to form water example. You have the AA molecule sitting there and the BB molecule sitting there, minding their own business. Okay, let's say you toss a match in. For a brief moment in time, right here, the bonds are rearranging, and let's say A slammed into B at the right speed and the right angle, the right orientation, and for a brief second of time, fraction of a second, 10 to the minus 15 seconds, you'll have an activation complex, and then it will slide down the energy hill, assuming it's exothermic, and it'll form the products over here, 2 molecules of AB. So that's what an activation complex is. It's just for a brief fraction of time, the rearrangement of bonds within the reactants. And we're interested in that because that is the key to understanding the reaction rate of this hypothetical reaction. Okay, your book describes 4 factors which affect the rate of reaction. Number 1, temperature. Generally speaking, as the temperature goes up, the rate goes up. As a rule of thumb, for every 10 degrees Celsius that the temperature is raised, the rate doubles. This is just a rule of thumb. Okay, why is that? Because a reaction needs lots of collisions, and the collisions have to be at the right orientation. So what does raising the temperature do? It speeds up the atoms and molecules in the reactor, and presumably then would increase the number of collisions, and therefore would increase the rate of the reaction. Number 2, concentration of reactants, the A and the B in that equation. Well, if we increase the concentration, the rate should go up as well. If we increase the concentration of reactants, very important. Increasing the concentration of the products would hurt you, but increasing the concentration of the reactants will help you. It'll increase the rate. And why is this? Well, think about the collision model. That would result in more collisions between the reactants, and therefore, presumably, the rate should increase. Number 3, the surface area of the reactants. If we increase the surface area of the reactants, let's say the charcoal that we're using in making black powder, if we grind that charcoal up to the consistency of fine flour, we're increasing its surface area, because a bunch of small particles have more surface area than the same mass of large particles. And so the rate should go up. It's going to increase the surface area that collisions can occur. And number 4, using a catalyst. Using a catalyst, there are many catalysts. We've used several in labs thus far. We've used manganese dioxide, that black powder that's used as a common catalyst. We've used sulfuric acid as a catalyst. Using a catalyst speeds up the rate. So you guys did a paper on automobile catalytic converters. And what is that doing? It's using platinum and palladium in very thin layers, because platinum is very expensive, inside a catalytic converter to speed up the rate at which the nitrous oxides and the carbon monoxide are getting oxidized in your catalytic converter. Okay, this gives us a graphic visual of what a catalyst is doing. In one of our previous labs, we took hydrogen peroxide, and we're going to break it down and hopefully make pure oxygen gas, because we wanted to experiment with the oxygen. The other product is going to be water, which we didn't care about. Well, if you recall, the minute we put some black powder, manganese dioxide, as a catalyst in that beaker or in that test tube, the reaction sped up and started producing oxygen very, very quickly, actually. So manganese dioxide is acting as a catalyst. What is it doing in terms of an energy diagram? It's shaving the mountain off. It's shaving down the activation energy hurdle or hump there in the middle. And it's allowing the reaction to proceed a lot faster. The catalyst itself is not used up in a reaction. It returns to its original state and then can be used again and again and again. In an automobile cat converter, we're using a heterogeneous catalyst. Platinum, palladium, I think there's also rhodium. And this is lining the surfaces of the catalytic converter, and along come the nitrogen and carbon molecules down your exhaust pipe, and they bind briefly to the surface, and the bonds are weakened, and then oxygen can combine with them and form other products, nitrogen dioxide and carbon dioxide, before going out your exhaust pipe. In biochemistry, the catalysts are called enzymes. So in the molecules of life, we refer to catalysts as enzymes. Enzymes can be a blob, just a folded up protein like this that has an active site somewhere that's very carefully configured so that another molecule can come along and bond to that active site. Or enzymes can be very complicated machines, nano machines in the cell. There are many molecular machines in the cell. Next topic, rate determining step. Okay, let's take the reaction between hydrogen gas and iodine gas, which produces hydrogen iodide, or if you bubbled that through water, you would get hydroiodic acid. Well, there's a couple possibilities of how this reaction could actually proceed. Perhaps it's possibility number one, where a molecule of iodine, I2, that's two atoms of iodine bonded together, collide with something and break apart into two iodine atoms. And then step two, maybe those two iodine atoms collide with a hydrogen molecule and form our product, hydrogen iodide. Well, maybe that's true, but maybe there's another possibility when you think about it. Maybe the iodine molecule splits like the other one and forms two individual atoms. And then maybe one of those combines with a hydrogen molecule to form kind of an intermediate entity there, which then continues on and combines with the other lone atom and then becomes our product, hydrogen iodide. Well, perhaps that's the case. And maybe this is the slow step, what we call the rate determining step. Getting that to split in half, you could imagine it would have to collide with another one at the right angle and very high speed to get those bonds to break. Maybe that's relatively slow, but then once we produce this unstable atom, this probably would combine fast, and then this would combine fast because these are sort of unstable. Maybe this is the slow rate determining step. That would be sort of logical. Well, this is the step we're concerned with then in coming up with a rate equation for that reaction. Well, it turns out with that particular reaction, the rate is equal to the rate constant times the initial concentration of hydrogen gas to the first power times the initial concentration of iodine in moles per liter raised to the first power. Turns out that actually is the rate equation. Where we use square brackets in chemistry, it means the molar concentration of something in moles per liter. Okay, well, in reality, that should say in reality, the exponents must be determined experimentally. So we don't just assume that's a 1 there and that's a 1. Have to be determined experimentally, which we will do down below. So the important thing here is the generic rate equation for this reaction takes the form rate equals a rate constant, lowercase k, little k, times the initial concentration of the reactants raised to some power. That is the generic rate equation. So that would hold true for any reaction. And the exponents are what we need to determine experimentally, along with the rate constant. The x and the y can be 0, could be 1, 2, 3, could be 1.5. So they need to be determined experimentally. So here's how you would determine the actual rate equation experimentally using this reaction. 2 molecules of nitrous oxide plus chlorine, molecule of chlorine, would yield 2 molecules. I believe that would be nitrogen hypochlorite. So step one, you collect some reaction data in your home lab. So you do 3 trials, and you vary the initial concentrations. So you do trial 1. You start out with initial concentration of NO of half a mole per liter. You start out with initial concentration of chlorine at half a mole per liter, and you observe a rate of 1.9 times 10 to the minus 2. Now, you do trial 2, and you vary this. You see, you double one of the reactants. You hold the other reactant constant. So you double the initial concentration of NO, but you hold the chlorine concentration constant. And voila, you observe a rate that's 4 times faster. All you did was double the NO concentration here, but you observe a rate that's 4 times faster. Very interesting. Well, you conduct a 3rd trial. You hold the initial rate of that reactant constant, and you double the other reactant. And voila, look, you doubled the rate. You went from 7.6 to 15.2 times 10 to the minus 2. So you end up doubling it. So what does that tell you? Well, the generic rate equation has to look like that. Reactant 1 raised to a power and reactant 2 raised to a power. Well, think about what's happened here. You doubled here in trial 2. You doubled the NO concentration, and the rate quadrupled. What does that mean? It means this exponent right here has to be 2. It has to be squared. Because if you're doubling the initial concentration of NO and the rate quadruples, that has to be squared. What about the chlorine? In other words, what about this exponent right here? Well, when you doubled in trial 3, you doubled the initial concentration of chlorine, but you held the other one constant, and the initial rate of the reaction doubled over here, 15.2. You doubled it, and the rate doubled. That means the exponent has to be 1. So we talk about reaction order. The reaction order is 2 with respect to NO, and the order of the reaction order, is 1 with respect to chlorine. That's what the term reaction order means. Now, we still have one more unknown, and that's the reaction constant. So this is how you calculate that. Use one of the trials, plug in the rate that we got for that trial, and solve for K, because we know what the concentration of each of the reactants was. We know what the exponents are. The only thing we don't know is little k, and so you can rearrange and you can actually get the rate constant from using one of the trials. I happen to pick trial 3. That's how you get the rate constant, and then you can write the actual final rate equation, rate formula for that reaction. You know, the rate equals this constant times NO squared, the initial concentration of NO squared, times the initial concentration of chlorine in moles per liter to the first power. And again, the reaction order, important term in kinetics, is the exponent. It is the exponent. So we say it's second order with respect to NO and first order with respect to chlorine. So going back to the questions, we answered question 1. Question 2, according to the collision theory, what 3 conditions? You must have lots of collisions. They must be at an adequate speed for the reaction to occur. The collisions must be violent enough. And the collisions have to be at the proper orientation. Those are the 3 conditions. What is meant by the term activation energy? We just explained that. What is meant by activated complex? We covered that. Describe how a catalyst influences the rate. How does it work, and so on. We just covered that. Define homogeneous and heterogeneous. A heterogeneous catalyst is in another phase. So an automobile catalytic converter where you're using a thin layer of platinum, let's say, as a catalyst, that would be heterogeneous because The exhaust gases are in the gas phase, but the catalyst is in the solid phase. A homogeneous catalyst might be where we used manganese dioxide and we put it in a solution of hydrogen peroxide. So they're both in a liquid solution. They would be homogeneous. That's the difference. Question 7. So this is asking temperature, surface area, and concentration. We covered that in our initial discussion. Okay, 8. Consider this reaction. Here's the reaction diagram. It's asking some true-false questions. And we covered all this in our discussion. You just have the reactants here, and they have to go over a very large activation energy hump or hill, and then you'll get the products over on this side. And so this would be an exothermic, that's your delta H there. This isn't your delta H. Don't count the activation energy. That is not your delta H, your heat of reaction or your enthalpy. The enthalpy of reaction is just the difference between the starting point and the ending point. So I believe you can answer all of those. And it's in E if the rate law is given here, then doubling the concentration. So it's going to ask you some rate questions, and we did discuss that at length in our initial discussion. Ignore question 9. Don't do question 9. It's getting at the half-life of a reaction, and I'm not going to test you on that. Question 10, the formation of hydrogen gas can be written here. So taking 2 atoms of hydrogen, which would be very, very unstable and wouldn't last very long, and they're going to combine into a diatomic molecule, hydrogen gas, H2. All right, you're given 2 containers. You can count the number of atoms, 1, 2, 3, 4, 5. So there's 10. There's 10 atoms there, and there's 10 over here. And it's telling you that it's second order with respect to H. So what does that mean? It means the generic rate equation would be H concentration to some power, right? So it's telling you it's second order. It's not telling you what the K is. You don't care to do the problem. But it is telling you that that's squared. Right, the rate equation. Oh, I guess I just did A for you. So I will let you answer the rest of those. 11, you perform some experiments for this reaction. And you determine that the rate law has this form. And it gives you 3 what-ifs and then asks you a simple question. And we talked about that at length. And here's some California standards test questions, which, just looking them over really quickly here, they look pretty straightforward. And we talked about all of these. See, here's kind of a multiple choice. We talked about all of these in our initial discussion. So if you have any questions about this assignment, please let me know.